d3x epsilon mu nu sigma e mu I f mu sigma I, like that. All right? So in particular, you can see that E appears as a Lagrange multiplier. So when you do the variations of the action with respect to E, you get the equations of motion F equals 0, right? Where F is the field strength, if you want. Okay, I'm not writing it. So that's the covariant picture. Then when you do the canonical analysis, so you have a pair of conjugated variables, ai of x, e, b, j of y, with the canonical Poisson brackets that are epsilon ab, delta ij, delta two-dimensional x minus y. Right? So people often introduce the sort of electric field. So this is gravitational theory, but we introduce E, B, J, which is epsilon B, A, E, A, J, like that. Right? Where epsilon is the completely antisymmetric tensor. So it's important to keep in mind that this gauge field or connection, together with this sort of electric field, is the phase space, the same phase space that you find in all gauge theories. I mean, most of them, especially Yang-Mills theory. So, for example, in electrodynamics, you would have here the gauge field, and here the electric field. But they would carry only the A and B indices. They wouldn't have I and J's, okay? In electrodynamics, you have delta AB, delta x minus y, like that. And these objects are basically the same in the two theories, except that now you have a collections of A's and E's that transform into SU2 here, okay? So here there would be U1 basically, because it's a one-dimensional group, you have no indices. So there would be U1 gauge theory. Then you want to do a quantization. Okay, so yeah, the main, yeah.
Okay, so you have SU2 in the case of Yang-Mills, but what you really have in the case of gravity is SO3. It's not SU2, right?
Doesn't really matter, yeah. I mean, difference would be very technical. Yeah. So the main difference between Yang-Mills with SU2 and gravity with SU2 is the Hamiltonian. So the phase space, that is the arena where you play, is the same. But the constraints in the Hamiltonian are different. Okay, in Yang-Mills or electrodynamics, the Lagrangian is F squared. And here it's EF, so it's quite different. Then you want to do a quantization, which means you want some phase space, some functions over the phase space to become operators in the quantum theory. So to do that, you cannot do that for any phase space function. I think Bianca Dietrich insisted on that. So you have to choose a family of functions that you will promote to quantum operators. So you probably introduced the holonomies, which are, so let's write them h gamma of A. So it's the path-ordered exponential of minus integral of A along gamma. So A is a one form, so you can integrate it naturally on a one-dimensional curve on a path, gamma. And then you take the exponential, but because it's non-abelian, you have to take a path-ordered exponential. That's a detail, basically. And so what's the meaning of this holonomy? That, so you have your space-time like that, and you have a point somewhere, x, and over each point of your space-time, you have an internal space that is all3, basically, or the Lie algebra as you do. So here you have the space all3, and if you have a vector on that space, v at x, well, and then I give you another point y with another vector v or u at point y. So you want to compare them together, but they do not live at the same space-time point, so you cannot compare them. What you have to do is to transport one of them to the other, and then you can compare them, like take the inner product or something like that. All right? So if you want them to speak to each other, you have to transport them. So you choose a path, gamma, and you act with your holonomy along gamma on this vector v. So you form a new vector, h gamma v at point x, h gamma minus 1, and that's your vector v at point y now. Okay? So that's the geometric meaning of the holonomy. It's used to transport objects. And because it transports objects between different points, it should transform itself in a consistent way with that parallel transport notion. So the transformation, when you do gauge transformation, yeah, h gamma becomes g at the endpoint. So let's say y is the endpoint of gamma. G of y, h gamma, g of x minus 1. Okay, so g is an SU2 field on your spacetime. And when you do gauge transformation, this holonomy transforms only at the endpoints. Okay. So that's a brief summary of what you guys saw. On the previous episodes. Now what you'd like to have is to build some canonically conjugated variables to the holonomies, right? It's like you now have some x and you want the piece, you want the momentum. So I'm going to rewrite the Poisson bracket, but now in the definition of the holonomy, you integrate A, like that. So what you will have to do is to integrate E also, and it's one form, so I'm going to integrate it along a one-dimensional curve. So I'm going to have something like integrate of a gamma star of E. So this is very sketchy at this point. And so that should give me integrals over gamma and gamma star of epsilon. Let's do it, yeah, epsilon A, B, all delta 2, x minus y. So if we can make sense of such a thing, you know, then the right-hand side of the Poisson bracket will be integrated along gamma and gamma star, so there should be something like 1 here, all right? But because there's an epsilon AB in the Poisson bracket, it means that gamma and gamma star should, cross each other. They shouldn't be parallel or tangential, okay? So to each holonomy, I want to associate a conjugate momentum. So if I have gamma like here, that's gamma, and here, that's gamma star, I'll define E of gamma like an integral along gamma star. EA gamma star of S gamma dot star A of S ES. Okay, so I'm integrating E because it's a one form. I just integrate it like that on a one-dimensional curve, right? But I told you these guys, they have an index in SU2. And the transformations depend on the space-time point. So I cannot sum them at different space-time points just like that. I need to transport them consistently to compare them to each other, basically, to sum them. Okay, so what I have to do is to choose some reference point somewhere. And every time I have some EI at a point gamma star S on that curve gamma star, I have to transport it to my reference point. And for each of them, I do that. Okay, then I can integrate. So there's one way to choose your reference point conveniently, which is to choose that point here, the starting point of gamma, basically. Okay, so I'm going to denote the parallel transport from that point to that point. So I have to choose a set of paths to do that. So I do it like that. Okay? I always go to the crossing. So this is H gamma star of S. And here I should put gamma star of S minus 1. Okay. So that's my definition. Well, so there's no I, obviously, because I act with the holonomy. So the transformation under local rotation gives you E of gamma becomes G gamma at 0, E of gamma, G gamma at 1, minus 1. Right, and this is valued in, the cos triad here is yeah. So yeah, I was about to comment on that precisely. So this object lives in the Lie algebra as you do. So here I act with the adjoint on E with my holonomy. So I'm still in the Lie algebra of SU2. So this object lives in the algebra of SU2. So maybe I should give you 2-3 minutes recipe for SU2 calculus. So a basis of 2x2 matrices is provided by the identity and the Pauli matrices, sigma 1, sigma 2, sigma 3. Okay, that's the basis to expand any 2x2 matrix. And so, for example, I have, if A is a 2x2 matrices, or let's say, to avoid confusion, M. So I can expand it like M0 on the identity plus M1, sigma 1, plus M2, sigma 2, plus M3, sigma 3, like that. Okay, so to get the coefficients M0, M1, and so on as functions of M, you need to know the scalar products between the Pauli matrices. So it's trace of sigma I equals 0. These are traceless matrices. And trace of sigma I, sigma j equals 2 delta ij. Okay, so if I take the trace of M, all these guys go to 0. So I'm left with trace of M equals 2M0. So you get M0 as just the half trace of M. And trace of M sigma I. Well, so you multiply by sigma I, which means here the trace gives you 0, because trace of sigma I is 0. And then you apply that formula here. So you get 2 Mi. Am I right? Yeah, I'm right. Yeah. Okay, so you know the coefficients of the expansion in terms of the traces of M. Yeah, in particular, also, there's an interesting formula that sigma I times sigma j. So it's a product of two 2x2 matrices. So itself, it's a 2x2 matrix. So you can expand it onto that basis. And that gives you delta ij times the identity plus I epsilon ijk sigma k. Let me write it like that. That's a formula that may be useful for you someday. So in particular, that formula applies to this guy here, EA. It's EAI. So you can choose different set of generators, and I noticed that Bianca Dietrich uses the T matrices, which are just minus I over 2 sigma I. So they have different normalization conventions, all right? Okay, so to answer your question, I removed the I here because that's an SU2 object, which is EI is the coefficient of E in that expansion, all right? And same thing here. So with that normalization here, you have trace of Ti, Tj equals minus 1/2 delta ij. Yeah, sure.
What happened to the epsilon?
You mean here? Yeah. That equation is very sketchy, with quotations, if you want. That was just to give you the feeling why I integrate over gamma star that crosses gamma like that.
So E gamma equals to
No, the definition is okay here. I will have to compute that Poisson brackets. That's the remaining of the lecture. Okay? So that's a definition here if you want. Right. And then the remaining of the lecture consists in calculating the Poisson brackets between the holonomy and the flux, basically. Yeah, several questions.
So how exactly do I find gamma star given gamma? Like, how do I decide exactly where the endpoints are?
So basically what we do here is we choose a subset of functions over the phase space. So it doesn't really matter. For each gamma, you choose a gamma star, and then you associate a flux, so it's called the flux variable. And then, well, you have to work with it, basically. So what you want here is that it intersects gamma at only one point, and the crossing is not tangential. And also by convention, we choose the crossing to be positively oriented. So gamma and gamma star are both oriented, and when they cross, you have no orientation. So that means epsilon AB gamma A. I have to remember. Gamma star, yeah, like that. Is strictly positive. So for example, if the two curves would cross tangentially, that would be strictly zero. And if one of the two curves has its orientation reversed, then there would be negative. Okay, so it's a convention. I choose the orientations in that way. So all this is reminiscent of what you can read in lattice gauge theory, where you take your gauge theory and put it on lattice. Then you have a given lattice, and that gives you the curves gamma and gamma star automatically, basically. Okay, now I want to calculate the Poisson brackets. Okay, so E gamma is E gamma I, where E gamma I is minus 2, yeah, minus 2 trace E gamma times Ti. And I want to compute, so calculate the algebra. So that's the algebra, the Poisson algebra generated by the Holomonies and the Fluxes. So you know that H gamma, the matrix elements AB together with the matrix element CD, the Poisson commute. And now we are interested in E gamma I with H gamma. So E gamma I is given by this formula with this trace of E gamma times the matrix Ti. So I'm going to write it explicitly. So that's an integral of a gamma star, and I have minus 2 trace of. Then I have together all the things that have that are 2 by 2 matrices. So here it's going to be H gamma gamma star S T K H gamma gamma star S minus 1 Ti. So that's my trace. And then epsilon A B B B K gamma star S. And this, we're going to call it F I K of S. Okay. So this F I K of S, defined like that, depends on the Holomonies, which means depends on the connection, but it's independent of the variable E. So I factorized the E here. Why do I do that? Because in this Poisson bracket, the only non-trivial contribution comes from the Poisson brackets between E and A here, from this formula. So in particular here, it only depends on the connection. So it's going to Poisson commute with the Holomonies along gamma. So the only non-trivial contribution is basically EBK gamma star S together with H gamma. So now let's have a look at the picture more precisely. EBK of gamma star S lives here on gamma star, and H gamma runs along gamma. So there's only one point where they can meet. Okay, and for convenience, I'm going to choose the parametrization such that here that point corresponds to S equals 1/2. I can choose it because the Holomie is invariant of the reparametrization. So I'm going to isolate the part of the Holomie H gamma that is here and here, and focus on what's near the crossing. So I write H gamma as H gamma basically from 1/2 to 1, but I'm going to put a small epsilon, so 1/2 plus epsilon. Then H gamma from 1/2 minus epsilon to 1/2 plus epsilon times H gamma from 0 to 1/2 minus epsilon. Okay, so I just decompose the holonomy. So I start from 0, then I go to 1/2 minus epsilon. Then I write a small holonomy between 1/2 minus epsilon and 1/2 plus epsilon, and then the remaining up to 1. So I do that, and because I only need the point close to the crossing, I can expand h gamma between 1/2 minus epsilon and 1/2 plus epsilon. So like 1, the identity, plus or minus, minus integral between 1/2 minus epsilon and 1/2 plus epsilon. Of gamma dot C S A C J gamma of S DS TJ. So I do an expansion like that because epsilon is very small. It's very tiny. So I can expand. Are you ready for the calculation? So then we can go E gamma I with H gamma. So it's minus H gamma between 1/2 plus epsilon to 1. Then I have a generated Tj, H gamma from 0 to 1/2 minus epsilon. So this term is basically this, and then I expanded that like that, but the one is completely irrelevant, Poisson commute with everybody. So I just wrote Tj, and then the last part here. Okay, that's the beginning. And then I have an integral on gamma star, and an integral between 1/2 minus epsilon and 1/2 plus epsilon. F I k of S epsilon BA gamma dot star A of S gamma dot B of S prime. It's a C here. Sorry. C. And then what I expected is Poisson bracket B K gamma star of S together with A C J gamma of S. ds prime. Okay, so I'm just gluing everything together. Mm-hmm. So this is minus delta BC, delta JK, delta, a two-dimensional delta between gamma star S and gamma of S prime. So here, indeed, I see that the only non-trivial contribution comes from this crossing, where gamma star of S is equal to gamma of S prime. Epsilon BA gamma dot B of S prime gamma. Okay, so then I have a two-dimensional integral with a delta function that is also two-dimensional. So it's certainly something like 1. So to do that more precisely, you have to see that I integrate over the variables S and S prime, but the delta function is on gamma star and gamma. So there's a Jacobian from that change of variables. So this delta function here is delta basically delta of S minus S prime. Let's write that. Yeah, so it's delta of S minus 1/2, delta S prime minus 1/2. So I told you I decided to set the crossing point to be at value S equals 1/2 for the two curves, for the two paths. That's the choice, just to write it conveniently. And then the Jacobian, well, it's 1 over the determinant of the change of variables here. So epsilon AB. So this contribution here is the Jacobian of the change of variables from SS prime to gamma star of S, gamma of S prime. then I can use my two delta functions. S is set to 1/2 and S prime 2. So I get something simple. H gamma times F IJ. Okay, and then I can send epsilon to 0. So I don't have this anymore. Is that okay? Yep. So I'm almost done. Here you see that I have a sum over J with a generator here and a coefficient here. So it's certainly going to be, I have to rewrite that. Yep. So here, so this delta function tells me that I get a contribution where gamma star of S equals gamma of S prime. So there's only one point, which is the crossing here between the two paths. So it means that, you know, I can, here it's my two-dimensional space. So I can parameterize it with S and S prime or with gamma of S and gamma of S prime. Okay. There's a change of variables between these two parameterization. So when the delta function is satisfied, it means that S equals 1/2 and S prime equals 1/2 too. That's just because I chose 1/2 to be the point of intersection. And then the Jacobian is this, basically, when you have such a change of variables. So this is exactly the point where having the two paths to cross positively matters, because in principle I have here the absolute value. So it depends on whether my crossing is positive or negative. I get a plus or minus in front of the whole expression. Okay. So Fij of 1/2 is, well, by definition, it's on top of the board over there. It's -2 trace of H gamma star 1/2 Tj H gamma star -1 1/2 Ti. then you have to remember that trace of something times a generator of the algebra is a coefficient of the expansion of the algebra objects in that basis. So I want to see Fij as such an object. And so I can use the cyclicity of the trace to write this as H gamma gamma star minus 1 1/2 Ti H gamma gamma star 1/2 Tj. So you know the trace is cyclic. So I do that. And therefore Fij 1/2 times Tj, this minus 2, trace of this Ti H gamma gamma star 1/2 Tj Tj. So that's H gamma gamma star 1/2 minus 1 Ti H gamma gamma star 1/2. If I'm right. So here what I did is just that, this object with red brackets here, it's a 2x2 matrix. And what do? I take its trace, I multiply it with Tj and take the trace. And then times the generator, Tj. So that's a Lie algebra element expanded onto the basis, onto this basis. So it's exactly this algebra element. Okay, so I can gather everything to say that E gamma I with H gamma is H gamma 1 1/2 H minus 1 gamma gamma star 1/2 Ti H gamma gamma star 1/2 H gamma. Now we have to see exactly what path do we follow. So we start here at 0, we go to 1/2, then we do that way, and so on. So we'll see what that gives on the picture. So we start at 0 here, go to 1/2, and then H gamma. Then we follow that holomony that brings you from that point to the starting point of gamma. Remember, that was the way I defined the parallel transport of the cotriad to define the fluxes. I start at some point at gamma star, and I go back to the start point of gamma. So if I have like that gamma star, and gamma, and the start point of gamma is here. That's gamma 0. Here it's gamma 1/2. So here I have h gamma from 0 to 1/2. And what is h gamma star of 1/2? So I'm on gamma star at point 1/2, and I go to the start point of gamma. So I go back here. So it's exactly the inverse of that object. It's h gamma 1/2 0 minus 1. Okay, I'm here, go there, come back. So that's the identity here. And then here, that's h gamma on 1/2 0. So my Poisson bracket is just h gamma ti. Okay, so the intermediate steps were complicated, but the final result is pretty simple. Okay, so maybe I should comment a bit on the way you have to understand that notation. It means that E gamma I with the matrix element of the holonomy, let's say matrix element AB, is the matrix element H gamma Ti AB. Okay? That's to be understood in the sense of matrix elements. Now the final thing to conclude the lecture today is to get the full algebra between the holonomies and the fluxes. So the Poisson brackets between two holonomies vanishes. The Poisson bracket between a flux and a holonomy is exactly that. And then we still have to find the Poisson bracket between two fluxes together. So the calculation I've just did was between one flux and a holonomy. Now, can you imagine what that gives if I have two fluxes? So it becomes a mess. But there's a way to circumvent that, which is to use the Jacobi identity. So we're going to trivialize the last Poisson bracket. What is E gamma I, E gamma j? So you can do Dirac calculation. You can do Dirac calculation. But I'm not sure you'll find anything very insightful. So, or you can use the Jacobi identity. Use Jacobi. So the Jacobi identity is something that has to be satisfied if you want a Poisson algebra, if you want some Poisson brackets. So, and reads, in the case we're interested in, it reads like E gamma I, E gamma j, together with H gamma, plus, and then I do the cyclic permutation. So I have H gamma with E gamma I, E gamma j, plus E gamma j with the holonomy, then with E gamma I equals 0. So it means E gamma I with E gamma j with the holonomy is so I can apply here the formula we just get before. So it's minus H gamma Ti with E gamma j, and so that's going to be a plus here, and then minus so that's plus H gamma Tj E gamma I. So I have this. And you remember the Poisson brackets that I wrote here on that side? They make sense in the sense of matrix elements. So here I should really see matrix elements and the products between H gamma and T. And here the same. So that's just like H gamma with E gamma j Ti minus H gamma with E gamma I Tj. Okay? So I can move the generator to the right. I cannot move it to the left because it doesn't commute with H gamma. And then I apply again the formula that I found. So it gives me H gamma Tj Ti minus Ti Tj. So that's the commutator. And the commutator between the T's is epsilon j I k H gamma k, like that. Okay, so there may be a sign mistake somewhere. No, that should be right. So this is satisfied. This is satisfied if E gamma I, E gamma j is sin j I k t k. Okay, so that concludes the calculation of the Poisson algebra for that case. So this is actually the Poisson algebra that you find a lot if you read some lattice gauge theory in the Hamiltonian formulation. you notice that this structure here is exactly the structure of SU2, of the algebra, with the same constants here. So somehow the theory mimics the fundamental symmetry group of the theory through the Poisson brackets. Okay. Well, that's all for you.